Hello, everybody. So, it's a very great pleasure to introduce tonight's speaker, Professor Slava Rychkov. I should disclose from the beginning that I have absolutely no intellectual credentials for doing this introduction, apart from a rather close familiarity with the timeline of what has so far turned out to be quite a remarkable career. So, Slava and I met in 1994 as undergraduate students in Russia, when we both had to attend military training lessons, which prepared us to be officers in the Russian Strategic Nuclear Defense Force, ready to rain terror and devastation on you. We bonded over a shared aversion to bootstrapping and to the pedagogic style of Captain Ivanov, which anticipated the intellectually arid conditions likely to prevail after World War III. To be fair, Slava got an A in the bootstrapping test, and I got a B. So I promptly escaped Russia and the economic hardships that accompanied the collapse of the Soviet Union to go to graduate school in America. But Slava at the time was a pure mathematician and was therefore immune to economic hardships. And also he was intellectually quite happy in Moscow, working in mathematics. His first paper was called Pointwise Multiplications in Weighted Sobolev Spaces on a half-line, and was published when he was a third-year student. So third-year students here, think about that. Undergraduate student, I should say. The downside of staying was that he had to complete the military program of training by going to a boot camp, living in barracks and goose-stepping some more in circles around ICBMs and silos. He said to me afterwards that that experience helped him achieve a clarity of mind that he had never experienced before and indeed never experienced after. This is a clarity on which obviously I have missed out on. Explains the differences between his subsequent career and mine. He wrote a mathematics paper in that camp. It was perhaps this increased clarity of mind that prompted him to decide to get out of the country finally, and to go to graduate school in mathematics in Princeton, where he worked with Elias Stein on harmonic analysis, was considered a superstar in the mathematics department, and where, interestingly, our trajectories intersected again. So a memorable experience of that time was when both he and I attended lectures by a brilliant Princeton string theorist called Alexander Polyakov. I remember we were both comprehensively fascinated by those lectures. It was an absolutely amazing experience. But Slava was the only one who actually understood what Polyakov was talking about. and so he decided at that point that he had had enough of pure maths, went to see Polyakov and asked to work with him. Those were the waning days of the 20th century, right? And so this was still the Enlightenment period in the world's history. So Princeton Mathematics Department said to him that this was perfectly fine. He could defend his PhD on what he had already accomplished, but it was perfectly fine with them if he hung out for another few years and just worked with Polyakov on gauge fields and strings. And so he, as a result, essentially completed a second PhD for the price of one, and went on to a postdoctoral stint in Amsterdam, where he became interested in such esoteric things as black hole production and quantum particle collisions. I am not sure, I haven't asked you, Slava, whether you had a hand in or received royalties from the famous, extraordinarily bad novel by Dan Brown called Angels and Demons, which dealt with this exact subject. So we'll leave that to explore later. So he then went to Scuola Normale Superiore in Pisa, where working with Riccardo Barbieri, he apparently developed more of a knack for connecting theoretical knowledge with experimentally relevant questions. So one of the papers he wrote, which was on something Alan will understand that, something called improved naturalness with a heavy Higgs boson, an alternative route to CERN LHD physics. This was written then and now has 750 citations, so clearly this worked. So he quickly became a superstar in particle theory, and so the University of Paris rolled out the red carpet all the way from Pisa to Paris for Slava to cross the Alps in the direction that was the reverse to the one previously taken by Napoleon, and to join the theoretical physics moment in Paris. But after a few years there, he succumbed to the residual attraction of the Alps and went to spend 5 years at CERN. Interestingly, just as he was thus ascending the particle theory Olympus, perhaps I should say Mont Blanc, his interests started shifting towards condensed matter theory, on which he promptly made a deep impression with his conformal Bootstrap program, of which you will hear more in this lecture. So for his achievements in this area, he was awarded something called the New Horizons Fundamental Physics Prize in 2014. This is a pretty good prize, not just intellectually, but also financially, as a result of which all our dinners in 2014 were on him. Even though they were dedicated to my so far unsuccessful attempts to make him see that 3D Ising model was just as passé as Sobolev spaces and mini black holes and Higgs boson, and the true intellectual challenges lay in plasma turbulence. I have so far failed in this program. So finally, last year, he went back to Paris, where he was elected to the Mitsubishi chair in high energy physics at École normale supérieure, and then became a Professeur permanent at Institut des Études Scientifiques in Bourg-sur-Yvette, which he tells me is a theory paradise. Although, as far as I can tell, it's but a pale imitation of an Oxford college. Apparently they have lunches, but not dinners. This said, I think it's safe to say that he has more or less joined the ranks of Les Immortels, and a shrine in the Pantheon is being prepared as we speak. He does not yet have a Légion d'honneur, but it's a matter of time before he receives that call from the Élysée. I'm glad to tell you, however, that despite this meteoric rise, he appears to have preserved the degree of sanity, which, as you can see, I haven't, which is clearly attributable to the difference in the degrees of our military training. However, to test this resilience to glittering honors, he's about to rise to the ultimate pinnacle of them all and become the 27th Ockham lecturer. So, ladies and gentlemen, I give you Professor Slava Rychkov, who will tell you in the welcome anti-reductionist vein that things big are not always made of things. So,
thank you.
Well, thanks, Alex, for this introduction. I hope it took you less time to write that than to me prepare my slides. So I'm not going to try to compete with the level of jokes. I'll just be happy to report that the only reason for you getting a B for goose stepping, that it did not occur to you that to goose step you need shoes, you cannot goose step in sneakers. Anyway, it's a great pleasure to be here, and it's a great honor to be 27th Ockham lecturer. So I'm going to speak today about mental schemes that we use in physics when we think about the connection between microscopic and macroscopic. So not all of physics is preoccupied with this connection, but there are some significant parts of physics, like particle physics, condensed matter, and statistical physics, which are definitely concerned with it. And so I'll describe the traditional ways to think about this connection, and then I'll describe an alternative mental scheme, the Bootstrap scheme, which has been around for a while, but it's only in the last 10 years it kind of rose to, it's starting to fulfill its promise. So so traditionally, it's kind of an implicit assumption that in physics, every phenomenon or every law that we observe it at a certain distance scale, a certain distance scale L, which is the scale which is set by the resolution of our experimental apparatus. But we usually think that the origins of this phenomenon, they are hidden, or we look for these origins at some more microscopic scale, A, much smaller than L. And so it's ingrained in, as any student of physics knows, it's basically ingrained in all textbooks that very often that to understand, we don't say that we understand a certain phenomenon is until we identify some sort of microscopic origin of this phenomenon. So we build a microscopic model. We don't always need this understanding, we don't always need this microscopic model to do physics at the scale L. But unless we have in mind some sort of origin, then we are usually not satisfied. We say, oh well, there's something we don't understand. And I mean, there are many, many examples that I'm sure that any of you can come up with. Perhaps I should quote at this stage Lord Kelvin, who I think in 1904 said that, precisely this, he said that we don't understand a physical phenomenon until we can build a mechanical model. Well, he said a mechanical model, but nowadays we say microscopic model. Well, let me just give two examples. So in condensed matter, suppose you do theory of magnets, and the microscopic origin of this phenomenon is, we think the magnetism is associated with individual electrons having individual magnetic moments, and then the magnetism appears as a collective effect of interaction between these individual electromagnetic moments. So that's a simple example. So particle physics furnishes a slightly different perspective on the same problem. So in particle physics, so particles that we observe, they're already pretty small, pretty microscopic, you could say, but we are never satisfied with the particles that we have at our disposal, so we try to smash them against each other, like nowadays it's happening at LHC, we smash protons, and then when we do this, some new particles come out, and we are trying to understand what are the origins of these additional particles, and usually we think that these origins, they are hidden somewhere at a still higher energy, which means smaller distance scale, where processes which turn some particles into other particles are supposed to be happening. And we are trying to understand what are these processes. So, fine. Now, there are, however, some phenomena or some particles that we call elementary particles. So I'm not going to try to give a rigorous definition at this stage, but just for starters, these are some phenomena that we are comfortable nowadays to accept as they are and not to look or postpone looking for further explanation for the time being. And for example, electron is an example of such a phenomenon. So as far as we know, electron is an elementary particle. It's a good elementary particle. And so so this search for elementary phenomena, for elementary particles, that's what drove the development of particle physics for many years, and it led to the development of the standard model of particle physics. So this is a table, and it contains 17 particles. I'm sure that many of you have seen this table. I'm not going to talk a lot about it, but I'm just going to highlight some aspects of it which are important for my story. So one aspect which may seem confusing is that many of these particles, most of these particles, are unstable. But that should not, you may be concerned, okay, how can you be both elementary and unstable? Okay, but you should also remember that the Mendeleev table of atomic elements also contains many nuclei which are unstable, and nevertheless they appear in the stable. So you can be both elementary and unstable at the same time. That's not a problem. So these are the elementary particles, and out of these elementary particles, many composite particles are built, and as you see, this table is not showing very well, but that's precisely the point. I can, there are hundreds and hundreds of the particle data group is compiling data about hundreds and hundreds of these particles, and I don't expect you to see this. And this brings me to the main question of this talk. So, why? Isn't this amazing that we can reduce this whole world of particle physics to a collection of elementary building blocks? So why does this happen? Well, this is not a very well-defined question, so perhaps a better question would be, could you imagine a world where it would be otherwise? What would an alternative world look like where it's would be different? So that's the question that I would like to discuss a little bit. And for this, I have to clarify a little bit about this concept of elementary building blocks, that's elementary particles. So the main properties of elementary particles is that, okay, the first property is that it's point-like. It does not have a size, does not have a characteristic size. But there's also a second property that it's supposed to be weakly interacting. So this is essential if you want to start taking these particles, elementary particles, and you start operating them as a Lego game, putting them together and form more complicated particles out of them, or vice versa, take a more complicated particle and to separate it. So for this, you have to be able to tell the identity of one constituent from the other constituent, and that's what in physics we call very weak interaction. And here I put this qualification, at least in some regime. That actually is an important qualification, because, so without this qualification, actually, some of the particles in the Stern-Wall table, you would not be able to call them elementary. And this concerns, so this is an interesting detail, and okay, I want to spend some time on it, because it will help us imagine what could be the alternative world. So this is the story of the proton. I understand that people here, most of the people here are aspiring physicists, undergraduates or professors. And so one often says that the proton is made out of 3 quarks, 2 ups and 1 down quark, 1 down quark. But actually, it's important to realize that this is true. This mental picture has certain limitations. So if you view proton at rest, or as we say at low energies, with small kinetic energy, then actually proton is not just these 3 quarks, but it's a strongly interacting soup, which includes, in addition to these 3 quarks, also a bunch of gluons, infinitely many gluons, and also some virtual pairs of quarks and antiquarks, which pop out of the vacuum and disappear into the vacuum. So, and these quarks are strongly interacting, so you cannot separate them. And so this would contradict my definition of elementary particles. In which sense is quark an elementary particle? Well, it's because there is a regime in the theory of quarks and gluons, which is the high energy regime. It turns out that the strength with which the quarks and gluons interact depends on the energy. This is a phenomenon called asymptotic freedom. And if you take, so what it means in practice is if you take a proton and if you smash it with a photon, for example, with a high energy photon, then the photon will seek out inside the proton, a point-like quark of a charge 2/3 times the charge of the electron. And in this process, the quark will be point-like and individualized, weakly interacting. So the existence of this high energy regime, it's very important because it provides kind of boundary condition for the whole theory of strong interactions, and it allows us to say that quarks as elementary particles exist. So, so now precisely you could ask the following question. I mean, okay, that's what happens in the real world, but could you imagine a world in which the proton would not be point-like, so it would not be point-like and hence it would not be an elementary particle, and yet you would not be able to identify inside the proton elementary weakly interacting constituents. So in such a situation, you would be forced to admit that this picture does not allow a reductionist description. So there are no elementary building blocks. So that's not what happens in the real world, but logically it's a possibility, and it's interesting to understand, why is it not realized? And well, now we have an advantage from nowadays to know that this is not realized in the real world. But actually, when in the 1960s, when people first started observing this whole panoply of strongly interacting particle, that table that was not visible that I showed you, that was one of the ideas that they were contemplating. And okay, now it's almost forgotten, but I think it's important to remember about it. So there was a physicist called Jeffrey Chu, who around 1960, when these particles, when the accelerators started producing more and more particles, and nobody had any idea where are all these particles coming from, how to think about them, so people were really confused. So he proposed this idea called nuclear democracy. So he said that, well, perhaps we should not try to take these particles and to try to reduce them and to say, okay, these are particles which are elementary and these are composite made out of elementary, but perhaps we should think that all of these particles are equally elementary, equally fundamental, or perhaps equally composite, but anyway, we should try to build a theory which treats all particles on equal footing. So he called it nuclear democracy. And well, this was an outrageous idea at the time, and many people thought it was outrageous, because in this case you would say, well, where do you start? That's just words, but how do you actually build a theory out of these words? And they tried to build a theory, and that theory was based on consistency requirements. So in the traditional theory, if you see two particles, okay, A and B, then you say, okay, well, it's because one of them is elementary and the other is composite, B is made out of A, or perhaps both of them are made out of something else. We should just look harder. Where are these constituents? But in Chu's theory, he said, well, it's just because that's the way it is. That's, you see these two particles because A could not exist without B and B could not exist without A. And you should try to formulate some axioms. So he tried to formulate some axioms. Most of these axioms were pretty reasonable axioms, so he said, okay, my theory should be consistent with quantum mechanics, with special relativity, all probabilities should add up to 1. So, things that people already knew at the time. And he was hoping at the time that this system of axioms only has very few solutions, perhaps a single solution, that is going to describe the real world. And he called this scheme Bootstrap, referring to the magical act of lifting yourself by the shoelaces. And for about 10 years, this scheme was intellectually dominating. particle physics. It was a confusing 10 years of particle physics. And okay, you say, well, in physics this is unusual, it's very unusual, that's not how physics works. But if you take analogy and if you look at what happens in mathematics, then in mathematics there are many, many examples like that you don't try to reduce something to more elementary constituents. And okay, perhaps the simplest example are the prime numbers. So if there are infinitely many prime numbers, and nobody will tell you that some prime number is more important than the other one. They are all equally fundamental, and you could say that every number is a product of prime numbers. So in some sense, these are elementary constituents, but there are infinitely many elementary constituents. So could something like that work in physics? That's the question. Okay, well, so how am I doing with time? What time did I start at? After you, because you had a long
20 minutes too. You've got another 40 minutes.
Okay, I'm doing fine. So this idea, this Bootstrap idea, it scored some early successes, and I'm just going to discuss one of them. So the simplest, strongly interacting particles are p mesons, the lightest strongly interacting particles. And then at some point, another particle was discovered, which is the rho meson, and nobody understood, okay, what is this rho meson, why is it needed? And in the Bootstrap scheme, the understanding that they gave for the rho meson was as follows. So they said, okay, we have p mesons, and the p mesons interact by exchanging a rho meson. So the rho meson couples to the p meson with a certain strength, which is called G. And by mediating the rho meson, there is an attractive force. And as you know, when there is an attractive force in the system of two particles, then you can form bound states. So hydrogen is a bound state of a proton and an electron. So here we have two p mesons, and they have an attractive force. So perhaps there's a bound state in the system of two p mesons. So the properties of this bound state, they will depend on the strength of the attractive force, on this coupling, and also on the mass of the rho meson, because this determines the range of the attractive force. And then, okay, so there is this bound state, but what is this bound state? It's like another particle. Oh no, you say, well, that's not another particle, that should be the rho meson itself. So the rho meson appears twice, both as a particle which mediates the attractive force, and the bound state, which is created as a consequence of this attractive force. So this is the Bootstrap idea. So the same thing appears in two places, and the self-consistency requirement is that it should be the same mass for the rho meson that comes out of the two places. So by the way, if there are any questions, you should interrupt. So this gives you an equation, gives you a mathematical equation for the strength and for the mass of the rho meson. You can solve this equation and you find the mass, and with a certain approximation which was good for the standards of those days, it worked. But then, so as I said, okay, there were some early successes, but then the program stalled a little bit because on the one hand, the equations were very hard to solve. On the other hand, the accelerators kept discovering more and more particles, and so the equations had to be constantly changed to accommodate all these newly discovered particles. So, and finally, what happened is that in 1970, quarks were discovered. And so the whole nuclear democracy program was basically abandoned overnight. So it wasn't done. So the microscopic approach, the usual microscopic approach won. So it's a sad story, but but nevertheless, well, it's important philosophical story because it didn't have to be this way, but the experiment spoke, and in the real world, that's the way it is. But now you can ask, okay, in particle physics, that's the way it is, but as we know, any good idea is true in some sense. So perhaps the idea of the bootstrap did not work in particle physics, but perhaps it applies in some other part of physics. And that's precisely the second part of my talk. So I'm going to describe how the same idea, the idea of the bootstrap, the idea of self-consistency, and the idea of treating infinitely many constituents on the same footing, found about 10 years ago, found an application in the theory of critical phenomena, in the theory of critical points, which belongs to a completely different branch of physics, to condensed matter physics. So critical points or continuous phase transitions. So now we are changing to a very different type of physics. So let me remind you the key experimental facts. So as I said, the area of application is going to be continuous phase transitions, critical points. But these are very special phase transitions. So the much more usual phase transitions with which we are familiar in everyday life are discontinuous. So the things like when you take a block of ice and it melts, or when you take water and it boils, these are continuous phase transitions. Discontinuous phase transitions, or otherwise called first order phase transitions. If you take water, and if you take a phase diagram of water, then in the phase diagram of water there are three phases. There is a solid, gas, and liquid. And the discontinuous phase transitions are happening, for example, between solid and liquid, or between liquid and gas. But there are two special phases, there's two special points in this phase diagram. One is this triple point, but that's not the one I'm going to be talking about. That's not the one where my theory applies. But there is this other point, the critical point, which is the end point of the line separating the liquid and the gas phase. And so this is called a continuous phase transition. So the point happening at the critical point. It's called continuous because as you approach this point along this line, the difference between the density of the liquid phase and the density of the gas phase goes to zero. So at this point, this difference disappears, and that's why it's called continuous. Another example of a continuous phase transition occurs in the theory of magnets. So here we also have a two-dimensional phase diagram. There's a temperature and there is a magnetic field on the vertical axis. And in this case, the line which separates two phases, so the physics picture is easier in this sense, in this case, in a sense. So if you apply a magnetic field and if the temperature is low enough, then the magnet is going to order, so you get the spontaneous magnetization. If you apply the opposite magnetic field, it's going to order down. But as you increase the temperature, this spontaneous magnetization is going to go down, m goes to zero, and that's why the end point of this line separating the two ordered phases up and down, again we call it a continuous phase transition. So this is the critical point which happens at a particular temperature for every magnet. So these are the two typical examples of the phase transitions, and as we will see later on, in some sense, this is the same example. So it's the same theory which describes these two examples. And so, so now I want to mention some features, some very important features of these critical points. And the most important feature is the existence of fluctuations which happen at all distance scales. So there are fluctuations of all sizes. So let me explain this. So here's a snapshot of a magnet. practice of a simulation of a magnet. So the dark and the white spots means the spins, the local spins pointing up and down. So you do this snapshots at 3 different times. And as you see, there are islands of up spins in the sea of down spins, and these islands, they have all you can see it by the naked eye almost, that there is no characteristic size. There are big islands, there are slightly smaller islands, even smaller islands, and so on. So this is what we call an absence of a characteristic scale. And fluctuations means that the shape of these islands constantly changes. And so this absence of characteristic scale is a very particular property of a critical point, which mathematically is expressed by saying that the critical point has scale invariance. So if you look at this snapshot, and if you increase the resolution, it will still look the same. It will still look basically the same. So this is scale invariance. There is also conformal invariance, which is a more nuanced characteristic of these snapshots, which I'm not going to define. It's some defined version of scale invariance, but I won't be able to go into the uses of scale invariance anyway. But if you are interested, then ask me later on. So this was for the magnets. And here the quantity which fluctuates is the magnetization, the local magnetization. Now if you look at the liquid near the critical point, then the quantity which fluctuates, the most evident quantity which fluctuates is the density. And here actually, so I have here several snapshots. Now you go to YouTube and you find beautiful videos of what happens, what the liquid looks like near the critical point. So there are 5 snapshots here which happen near the critical point, and here you see there is some milkiness, there is some fog going around, and okay, these are the fluctuations. But the most amazing thing happens precisely at the critical point, and then precisely at the critical point, liquid just looks totally milky. So it's not transparent at all, it loses transparency. And this phenomenon is called critical opalescence. So this is a very famous phenomenon. And so why does it happen? Well, it happens precisely because there are density fluctuations of all sizes, both small and large, and light scatters on them. So if you think about them, the intermolecular distance in liquid is very small. So the light wavelength is much larger than that. So for the light to scatter, there have to be density fluctuations as large as the wavelength of the light which scatters. And such fluctuations apparently are present in the liquid near the critical point. So this is critical opalescence. Okay, so I told you there are these fluctuations, and now we have to characterize the existence of these fluctuations not quantitatively, not qualitatively, but also quantitatively. So, and the way you characterize fluctuations quantitatively, you look at their correlation functions. So, for example, you can look at the correlation functions of the density fluctuation, delta rho, which is the deviation from average density. So since it's a fluctuation, if you average it, and here you can average either over time, or you can average over thermal ensemble. So the average value of this fluctuation is equal to 0. So it means that looking at 1 point correlation function is not interesting. But it becomes interesting if you look at the 2 point, already at the 2 point correlation function, and then at the higher point correlation function. So here I'm looking at the density correlation function. So I'm looking at the density fluctuation at 1 point, delta rho of some point R1, and delta rho at some point R2. and I average this product. So this is not going to be zero. Why is it not zero? Because if you have an over density somewhere, and if you look at density at the nearby point, then it's also more likely to be over dense there, and vice versa. If it's under dense, again, it's going to be the under dense. So it's an interesting function to look at, and now it turns out that this function behaves like a power law. So this is an experimental fact. So if you go to the critical point, you measure this correlation function, you will see that asymptotically, and by asymptotically I mean at distances much larger than the intermolecular distance, it will go as a constant divided by the distance between the 2 points to some power, to delta. This is just conventional notation. So delta is a number, and this number is called the critical exponent. So there are many different critical exponents, but that's one of them. So this is a key player in the whole game. So this number delta. So there are other numbers like that I'm going to introduce, but that's the first of them. So what do we know about this number? So it's a mysterious number. So what we know about it is, first of all, it's universal. So if you take two different liquids, if you go to the critical point, you measure this number, it's the same. We know this number experimentally to some precision. We know this number theoretically to some precision. So here I wrote what, as much as we know about this number. We know 6 digits. So according to our current understanding, this number is a fundamental constant of nature. I mean, it's just as fundamental as pi or e or square root 2. But unlike in the case of pi or e, when you can compute it basically to whatever precision you want, and by computing it to any precision means that you understand the number. So if you want, you can compute it. You don't have to, but you understand what this number is. So in this case, we don't really understand this number very well. So I mean, we have some reasonable theories about it, but we would love to understand it better. Like, is it a rational number? Is it an irrational number? Is it transcendental? Even things like that are completely beyond the reach of the theory. But this is a sort of fundamental parameter, and it'd be nice to understand it better. So what I'm going to tell you now is, this Bootstrap scheme, one of the outcomes of the Bootstrap scheme is the increase of understanding these sort of numbers, where they come from, both at the qualitative level, but also at the quantitative level. So we learn to compute these numbers better than it was possible. So similarly, in magnets, if you go to magnets, you measure again the correlation function of magnetization. You go to the critical point, so average magnetization is 0. You measure the 2-point correlation function, magnetization at 2 different points. You find again a power law, and you find a power law with exactly the same exponent. So it's an amazing fact of nature that 2 different systems, completely different systems, they just, in this regime, at the critical point, they are described by exactly the same sets of numbers. So when something like that happens, this is another manifestation of critical interceptor. The critical point of water is exactly the same as the critical point of magnets. So boiling water and magnets is the same. So when something like that happens, there is only one possible explanation. There should be some rigid mathematical structure behind, isolated, so not deformable mathematical structure. So mathematics is full of such structures, and there is a structure called conformal field theory, which is to our understanding, that's the structure behind this critical interceptor. So I'll say some words about what it is.
Can I just ask one? This is a probably stupid question, but obviously, you are giving these examples in terms of like liquids or magnets, but you could do the same thing, say, for like a superconductor. And when I mean a superconductor, I mean like a Higgs-1, right? and I can make that non-abelian as well, right? And so, like, I can think of the world we live in, which you were saying before, this thinking is sort of irrelevant, but I can think of it as a non-abelian superconductor that's very close to this critical point, right? As in the Higgs web is so small compared to, the fundamental scale, which to call the, distance between molecules, what I could call the Planck scale, right?
Yeah.
So, like, it's not obvious to me that, you cannot get some mileage out of, to understand that from this.
You're saying that once we understand this, then we can go back to particle physics and...
Well, what I mean is that, our world really is an non-abelian superconductor very close to that critical point. So, like, understanding, is it totally obvious that, there's no value for particle physics?
No, there's definitely some value, yeah.
It's not only condensed matter.
No. Well, certainly, yeah, but I think condensed matter provides the simplest setup to understand this, but once we understood it very well,
right,
we can go back to particle physics,
right,
and try to apply it there.
Sure.
Yeah. As you know, that's what I did initially. So what happens between particle physics and condensed matter, you just change from 3 to 4 dimensions.
Sure.
So, okay, fine. So where's the bootstrap? I promised you infinitely many fundamental entities. So here's where I'm going to introduce them. So you just have to do a slightly better experiment. So I said, okay, you look at this correlation function of density correlation function. And I said that if you go to distances large enough, you find that it's a power law. But now you make a slightly better experiment. So not only you measure the leading power law, but you measure also the subleading terms. And you find that actually it's not just one power law, but it's a sum. It's an infinite sum of infinitely many power laws over higher and higher powers. And so a more precise statement of what I already said is that all of these powers are universal. And so all of these powers are the equivalents of the infinitely many fundamental constituents. So, so what you can say is that in the system, so if you just say, oh well, let me look at the density. Density, like physically it looks like a natural thing to look at. Yeah, physically it's a natural thing to look at, but mathematically that's not the natural thing to look at. What this equation says is that in your system there are infinitely many eigenfluctuations. You can call it eigenfluctuations, like in the sense of eigenfunctions. And these are the fundamental things. While the density, it can be decomposed into this, anything else can be decomposed into this infinitely many eigenfluctuations. But by themselves, well, density is just there's nothing fundamental about it. It's just something that experimentalists can easily probe, but that's not what governs the self-consistent behavior of the system. And so this is the modern point of view. And so what we now go about, we are trying to determine as well as we can the parameters, these eigenfluctuation parameters. And by now, well, so this is a program, and so we learned already significant amount of information about these parameters. So we think that we understand the equations. I'm going to talk about the equations that these parameters satisfy, but that's not to say that we understand the full picture. This is still kind of, the picture is still developing in front of us. So the goal of the theory would be to understand all of these numbers. So where do they come from? So, okay, actually, concerning these numbers, both traditional theory, in a sense, and the more modern Bootstrap scheme, they would agree that these are the numbers which have to be calculated. But the traditional scheme would say that out of these infinitely many elementary eigenfluctuations, you would have to, out of these infinitely many eigenfluctuations, you would have to try to identify a few elementary ones which you have to understand really, really well, and everything else, all the other numbers in this table that I gave you, they should somehow reduce to the elementary ones by some procedure. So that was the traditional approach that people tried to apply for about 40 years, and it turned out that you can, it does not really work. I mean, it works, you can make it work on some sort of perturbative scheme, but then you realize that it's just voodoo. It's just trying to squeeze water out of stone. It's just not possible. It's not possible to reduce everything to the elementary fluctuations. There's nothing more elementary by one number in this table than the other table. And so in the Bootstrap scheme, you say that all of these fluctuation types are equally elementary, equally fundamental. And you try to run down consistency equations which govern all of them, which follow from conformal field theory that I mentioned. So that's the picture that you have. So you have that you have that your system, it's a superimposition of infinitely many fluctuating layers, and you should not really think that, okay, magnetization is the first thing that you come across, that's the only thing you should be thinking about. You will only be able to get a full description of the system if you think in terms of all of these layers, which are all equally fundamental. And so, okay, how much time do you still have?
15 minutes.
Okay. So this this equation, you've seen it. It was on the poster for my talk. So I would like to try to explain. So out of this equation, everything comes out. So this is the main Bootstrap equation. So I hope that you will be able to retain it. So so this is the self-consistency condition that we impose. So let me try to explain what this means. So it turns out that you will get a non-trivial self-consistency condition if you think in terms of correlation functions which involve 4 different fluctuating quantities. So that's unusual, because in physics usually 2-point correlation function that's all over the place, but 3-point correlation functions are rare, and 4-point correlation functions are basically unheard of, very hard to measure, very hard to simulate. But here, this is the heart of the matter. So the fact that this 4-point correlation function of 4 quantities exists, that's what makes everything tick. And so the idea is that you take this 4-point correlation function of 4 quantities, or 1, or 2, or 3, or 4. I mean, this could be magnetization, density, or any of the other infinitely many quantities. And you try to compute it in two different ways. But even one way is already somewhat unusual how to compute it. So it turns out that these fluctuations, they have so you make an assumption. So well, it's not an assumption in a sense. You say, well, I'm assuming that these are all fluctuations that there are. You have to assume that you are dealing with a full list of fluctuations. So if it's not a full list, let's just add another fluctuation to the list, right? So you have to assume that it's a countable list, but okay, as a physicist, that's not a big assumption. And then the following thing turns out to be true. So let's look at these two fluctuations of 1 and the 2. So I'm measuring 4-point correlation functions. But one way to think of the 4-point correlation function is the following. So you could imagine that you took your system, and where this O1 and O2 are located, you kind of shook it locally a little bit. And then where O3 and O4 are located, you kind of inserted your detectors, which read off the local characteristic of the system with those 3 points, right? So let's view the correlation function as some sort of propagation process where you shook the system at point 1 and point 2, and you read off what happened at point 3 and point 4. And so let's imagine that these 2 points, O1 and O2, are close to each other. Not coinciding, but close to each other points. Then you could say, I mean, you can say, that comes from the assumption of the completeness of a set of fluctuations, that by shaking the system at the points O1 and O2, the result of this shaking, you can decompose. You assume that you have a full list of fluctuations, so you should be able to decompose the result of shaking the system at points 1 and point 2 in the full list of fluctuations that you have. And this is these fluctuations that I call OK. So this is a very important point. So I call these fluctuations eigenfluctuations. So this, when you talk about eigenfunctions, then this brings to mind a linear theory. You take some elastic body, you shake it, and it just has some eigenforms that like an airplane, it has some eigenforms. But this system is not linear. So what makes it tick is that these fluctuations are not linear. So when you shook at the points of 1 or 2, then it's the same, these 2 fluctuations that you generate at the points of 1 or 2, they generate the fluctuation of the type OK. Well, actually not just one type, all possible types OK. And so, so I introduced these parameters that characterize fluctuations, which are delta K, which are these numbers, these power laws. So it turns out this is a novel characteristic of this approach, that if you want to pursue this approach, you are forced to introduce a new set of numbers, which here in this equation are called F1 to K, which describe the process of when you shake at points O1 and O2, then with which strength, with which amplitude are you going to produce each of these fluctuations OK. So now your system is characterized by 2 sets of numbers, 2 sets of real numbers, delta K's, and these numbers F1 to K. And then there's another set of numbers F3 for K, which tell you how this propagating fluctuation OK is going to transform itself to split again into 2 fluctuations that you read off at point 3 and point 4. So this is the left-hand side of this equation. And the right-hand side of this equation is exactly the same, except that you are saying that the very same process you should be able to describe by I arbitrarily split the 2 points, the 4 points, into 2 points where you shake the system and 2 points where you read off the result of the shaking. But I could split it the other way around. I could say, well, it's the same correlation function. I could view it as a result of shaking the system at 1 and 4 and reading off at what happens in 2 and 3. So exactly the same correlation function I should be able to compute also in this way. And so you get this equation. And there is a lot of bells and whistles that enter into precise mathematical formula that this equation describes. But what I want to say is that, okay, if you studied mathematics, you will probably recognize that this equation looks not unlike equations that, it's basically an algebraic equation. So in formal algebra, when you talk about, for example, a theory of groups, of finite groups, for example, the key property that groups satisfy is the associativity. So when you take two elements and you multiply by a third, you could do the same calculation in different order and you get the same answer. So what this equation tells you is that basically you can multiply fluctuations in the same way as you multiply elements of a group. Of course, group is a finite object. A finite group is a finite object. While here I'm talking about functions. It's a mathematically, it's a more complicated object. But you may have heard that that in the theory of finite groups you can classify groups. So in the end of the day, you prove a theorem that there is only a finite number of different types of simple groups. So it's not unheard of that algebraic systems can be classified. And so what we hope for is that this system, which is a mathematically well-defined system of equations, it basically has an isolated set of solutions. So if we learn to solve this system, then you can classify magnets, you can classify uniaxial magnets, there are different types of magnets, you can classify the universe, and so everything should come out from the system. So it was a big, I mean, it's a lot of wishful thinking because it's a complicated system of infinitely many functional equations for infinitely many quantities, and it's what we learned to do in the last 10 years is to solve the system with some approximation. So that's what Bootstrap is now doing. So we have the system for infinitely many fluctuations with some consistency conditions, and by solving this system, we find some numbers which are experimentally verifiable, so they agree with the experiment. So this led to progress on two fronts. So on the one hand, now we think we finally understand where these numbers come from. So we think that we reached a new level of understanding of what makes these critical points tick. And also along the way we computed some numbers that people could not compute with the usual traditional approaches. So it's amazing that these ideas of Geoffrey Chew, which were born in particle physics 50 years ago, were basically considered to be wishful thinking and were completely discredited and relegated to the trash bin of history. They now found second life in condensed matter physics, and to the point that even now particle physicists think that maybe they'll find it useful again. So this is, I think this demonstrates the unity of physics. It demonstrates that every good idea is in some sense correct, and it also demonstrates something that Alexander Polyakov, who inspired Alex and me to do theoretical physics 20 years ago.
You to do theoretical physics, me to give introductions.
Yeah. So as he noticed in his book that the garbage of the past often becomes the treasure of the present, and vice versa. So I'll stop here.
Thank you, Slava, for this lecture and for the thought that the trash bin of history may well be in the same universality class as the rest of the history. And so in that spirit, let's ask some questions. Who has questions?
So returning back to the particle physics side of it for a bit. When you talk about the fact that this bootstrap theory, did produce it, so you said predicted the mass of the road, for example, well, did it continue to predict the masses of other mesons and things like that? And can you show from the quark model that it should do that or not?
Well, the quark model, when it was born, it led to the same prediction with much greater ease, and basically, one approach you had to struggle a lot, and you had to, that model was also based on axioms of special relativity and quantum mechanics, so it cannot give you totally, it did not have to give you the answers that it was giving you were consistent answers, but it didn't look natural anymore. Why do you have to suffer to have a much better way to do it?
But it predicts the same values for masses and stuff like that, but does it predict, can you from the quark model derive the assumption you make in the bootstrap that the mass of this mediator should be the same as the mass of the bound particle?
Well, no, because in the quark model it's not, so the approximation that it's the low meson which is principally responsible for this attractive force that you make. It just turns out to be, it's good, it gives you a good answer in the zeroth approximation, but it does not give you a systematically improvable answer.
So if you, now when we can measure these things more accurately, we can find deviations from...
Yeah, no, you already had deviations.
Yeah, okay. I was wondering if so the reason, you originally abandoned it because you see quarks and go, okay, this is clearly a better way of explaining it, but then if you measure more accurately, you also find it doesn't predict well. Okay.
No, it was not predicting very well.
Already. Okay.
You got like 20-30% errors and so on. Which, if it's like the first paper, then it's okay, but if 10 years pass and you cannot improve it,
So you just mentioned at the end that the bootstrap may be coming back, having its use in particle physics again. That is in the form of conformal bootstrap, right?
yeah, so I did not mean let's go back to
No, I understand,
to strong interactions in applied bootstrap, but I meant in the context of trying to resolve the issues which beyond the standard law physics is trying to think about.
I was just thinking, because the conformal bootstrap is presumably a method that only works when you have a conformal symmetry, so at critical points. And I don't see how it's applicable to particle physics, except that maybe there is a conformal symmetry somewhere close to.
No, I mean, in the standard model, of course, there's no exact conformal invariance, but in beyond the standard model of physics, we daily contemplate some possible extensions of the standard model, which at high energies may have very complicated additional structure, which is posited in order to explain puzzles of the standard model. And you might think that those extensions of the standard model at high energies may be conformal, and the standard model may arise at low energies when that high energy theory is perturbed. Now, by itself, this does not solve anything, but it may play a role in some eventual solution. It enlarges your range of tools into this point. So in beyond the standard model of physics, it's very important to have many variables that you can tune, and you can say, okay, I add this, what does this, does it solve anything? Or, for example, the typical problem that we have very little idea about is why the Higgs mass is is where it is. Could the Higgs particle be, in fact, not a fundamental particle, but not an elementary particle, but a composite particle originating from some sector which might be conformal at high energies? So that's a typical kind of question that you might ask.
Sorry, you just said that theory can be conformal at high energies, but I thought that conformal theories don't depend on energy, so how come when you start at high energy and it's conformal and then you move flowing?
Well, if you what I have in mind in condensed matter, I'm more condensed matter or particle person. Particle. Well, conformal theories, they typically you can perturb them. Just like you take in the stem model, you can take first stem model with massless quarks, and then you add some extra couplings, and those couplings become important at low energies. So in condensed matter, you would say, well, let me first put my theory at exactly the critical temperature, but then let me detune the temperature a little bit. Then the theory is no longer exactly conformal, but there's still a big range of length scales where you don't notice that you detune the temperature. So in this sense.
In the fundamental equation that you showed, I mean, the equality was based on the fact that nothing happens between all four of them intrinsically, right? That you can somehow split it into two ways. Why should it be equal? Why shouldn't it be an effect that comes in the full correlation for the first time?
Why not in 3, for example?
Well,
because there is a technicality here that because of the conformal invariance that I did not explain, it turns out that in the technical language, so 3 points by conformal invariance you can assign to any 3 positions. So it just means that in a conformal field theory, 3-point correlation function is, in a sense, kinematically trivial. So you don't get any non-trivial consistency condition. But, so the first non-trivial consistency condition comes at 4-point value. So that's why 4 points. Concerning to your other question,
but then why don't, in the same way that you introduce suddenly the new one, Fij or something?
Yeah.
Well, how come you don't have to introduce Fijks and then get...
Well, because so you are saying why can't we be additional conditions at 5 point and so on? Well, because you can show that this equation that I wrote, if you impose it for all possible 4-point correlation functions, then it basically says that the algebra of fluctuations is associative. And once it's associative, then this kind of equation is going to be satisfied for all correlation functions, for any n-point correlation functions. So 4 points is both necessary and sufficient as long as you pose it for all different types of fluctuations.
And this is valid in any dimension, it doesn't depend on the dimension of...
This is valid in any dimension, in 2, 3, 4.
So, is it immediately clear that the 2 examples that we had at the beginning, they both showed the same periodic exponent, that it's immediately clear that if we solve such a system that there is only, is it because they're both in 3 dimensions and there's only one system of equations that we have to solve for 3 dimensions that will solve everything, or might it be that there are other systems of equations that we have to solve for other processes?
No, it's not at all immediately clear. It's no, it's not immediately clear. It didn't have to happen this way. What is definitely true is that what this approach suggests. So by reducing to conformal field theory and by arguing that the equations of conformal field theory only have visibly a small number of solutions, you already kind of know, so this proves that any critical theory should fall in one of the universality classes. What you show is first is that there are few universality classes. Then you know that there has to be some correspondence between experimental critical systems like liquids, magnets, the universe, and the non-CFTs. But which corresponds to which? In a sense, it's a dirty question. So it's an experimental question. So you could put it. Analogy that you could use is that imagine some complicated function and you prove there is only a finite number of local minima, and then you start at some random point and you want to go to a local minimum. Yeah, you know that there are only finitely many points that you can end up, but where exactly you will end up, it depends in the sense where you start from. And so what I'm saying is that the magnets and the liquids, they basically start in the basin of attraction of the same local minimum. But I can imagine that you might probably hook up a weird magnet, which nobody cooked up so far, that would end up in some other minimum in different basis of attraction. So there's no law which says that it cannot happen.
So maybe a variation on that question. Do you understand the domain of validity of the universality that you described there? At which point does it break down?
We understand it pretty well. So once you solve for the universality class, once you solve for this conformal field theory, you can test, in a sense, whether it's universal or not. You can test post factum. So, for example, I gave you a list of operator dimensions of the scaling of these critical exponents that come out of the calculation. So whether the theory is going to be universal or not, you can check post factum by looking at this list. For example, the fact that on this list there are only two numbers which happen to be less than 3, so this and this. It turns out to be in a subtle way responsible for why this is the right and universal solution. Because these numbers they correspond to two directions that you need to fine-tune to get yourself to the critical point. So the fact that there are these two numbers which are less than 3, it corresponds to the fact that the phase diagram of water has 2 dimensions, P and T. So there are some interesting connections that you can make, interesting consistency checks.
So your system of numbers would be valid for 3-dimensional, strongly coupled systems which are close to critical.
Yeah. So here there's some global symmetry. So we're going to do some technical directions. So there's a global symmetry Z2, which is built in this tables as well. So I classify all my operators into Z2 odd and Z2 even. So there is some. So every universality class is characterized by a number of discrete labels, like the number of relevant operators, the global symmetry, and yeah. So these are the important labels. These are the important labels. So you could try to argue that any theory which has this global symmetry and this number of relevant operators should fall to this universality class.
I guess that makes sense to the extent to which, the far infrared EFT should, the way we build EFTs is by declaring what the symmetries are and then, writing all the operators that are consistent with the symmetry, right? And I guess when you're probing the regime of infinite fluctuation length, that's the sort of all you care about.
Correlation length, yeah.
That's a far infrared, right?
Yeah, that's true, but I wouldn't call it limitation in universality. Yeah, universality happens. So I guess the question was like, to what extent do we understand universality? Maybe I misunderstood the question, but for example, we know exactly which things are universal and which things, because universality has some limitations. So not everything is universal. For example, here I had some constants here, Ci. So these constants are not universal. So if you take two different liquids, then these exponents are going to be the same, but the constant Ci are not going to be universal. But we know exactly what is universal and what is not.
But this is the same kind of, isn't that the same kind of, UV dependence that you get, like
exactly.
As you run down, say, like.
Exactly. These constants are what so I said delta rho can be expanded in eigenfluctuation, but the expansion coefficients are not universal. You're totally right.
You mentioned that about the classification of any group and maybe the classification of this bootstrap algebra. Do you think it's like a really approachable problem that could be solved, or is it impossibly hard?
Well, we made some significant progress in solving this problem in the last 10 years. A full classification is probably very hard, but classifying operator algebras with a small number of relevant operators and with some particularly important global symmetry groups, I guess there's going to be further progress in the next 5 to 10 years. So, full classifications in mathematics are very hard, but for physics, from physics perspective, definitely there's going to be further progress.
One question, you don't have to ask these terribly clever questions that you can ask.
You can ask me a silly question.
You can. Oh, there you go, silly question.
Take the silly question. Can you tell me about that three?
I'm sorry?
You've got all these complicated, possibly never-ending numbers, and you've got a 3 sitting there.
Well, that's actually this table is also fully visible. That's a very nice catch. Indeed, this is exactly 3, and it turns out that this 3 is related to the fact that the microscopic theory from where this critical points originates are theories with local interactions. So that the magnetic moments interact nearby and that the molecules bump around nearby. So when you go to the critical point, then this locality, it becomes, almost all of it becomes invisible because you get these power laws, and the power laws are long range. And the only thing which survives is this 3, and it is 3 because it's there is one particular fluctuating quantity which is called the stress tensor density, or the energy momentum density, which corresponds to the conservation law of energy and momentum in the system. And in theories with local interactions, that quantity, it has always this exponent precisely equal to 3. So it's a very important property, and actually it plays a role in the solution of the conformal theory.
So you see, Slava, when a Merton student tries to ask a silly question, it invariably turns out to be profound. Sustaining excellence, ladies and gentlemen.
No, I was asking you to ask a silly question.
Oh, well, that's why I demurred. Well, there. Please. No, you raised your hand, yeah?
I raised my hand.
Yeah,
That's a really silly question. I was just wondering, going back to this particle physics. So you have, I think, 17 elementary particles. Is that what it is?
Yeah.
Is it, in some sense, proof that they are elementary, or is it just that it hasn't been shown yet that they actually consist of even smaller ones? Because why would there be 17? Why is there a philosophical reason why we just want to be there to be one or something like that?
Would you prefer more like 42?
42 is good. 1 is even better.
No, it's not proven that they are. It's not proven that they're elementary. Given that this is an Ockham lecture, so let's say we have a theory, which is the standard model, which shows that nothing much would break if we assume that these particles are elementary and remain elementary up to incredibly high energy scale, much higher than the one that we can ever hope to probe in the near future. So, of course, we hope, in a sense, we hope that they are not elementary because in physics the progress is achieved by making simple assumptions and then showing them that they're actually wrong, and then you have to change your assumptions, and then you discover new laws by more complicated laws by breaking your old simple laws. But no, right now we think that right now, to the best of our knowledge, they are elementary. Nothing contradicts this assumption.
Okay, please.
I mean, Alex talked a little bit in his introduction about how the two of you went in different directions after your in your theory focus after your string theory lectures. But I'm just thinking an obvious example of a system that's self-similar on different length scales would be turbulence. And also, what does conformal field theory and conformal bootstrap have anything to say about that?
I haven't planted that question.
Well, no, thanks. This is a very, that's been the subject of many discussions over
dinners that you paid
over port that we had with Alex over a number of years. Yeah, it's fascinating to think that perhaps, if not conformal field theory, then the idea of self-consistency could play the role in some understanding of the theory of turbulence. So indeed, the theory of turbulence is traditionally built by focusing on fluctuations of a handful of quantities, for example, the velocity field. And perhaps one should think wider. One should try to introduce more quantities. But then this has not been done yet. So there's actually one paper by Rychkov and Falkovich where they develop some ideas, but I think there are no concrete results yet. Perhaps one day. But there's no conformal invariance in turbulence. So if the solution exists, it's not going to be exactly like the one that I described, but it may be inspired by similar logic.
All right. So on this note, right, there are clearly still problems in physics that neither have been solved by Slava or are likely to be solved by him in the next 3 weeks. and so some of us can focus on them during the next stage of this event. So before we thank Slava again, let me tell you that certain simple assumptions that we make about these lectures still hold. Those are that after this we're going to be having dinner. We are assuming quite reliably that there will be wine at that dinner. That is served to you courtesy of the physics tutors, so grateful. As usual, the rule is that the speaker at dinner has to be protected from having to talk to the people that he has to talk to all the time anyway, by undergraduates who will have further opportunity to talk to him and to each other about what they have learned. So let's thank Slava again for coming here, and